Okay, let's go. So my name is Brett Slatkin. I'm a software engineer on the Google App Engine team. I'm here to give you a detailed look on offline processing on App Engine, what that means, where we are, where we're going, what's changed in the last few months, and kind of give you an overview so you can use some new tools with App Engine to accomplish tasks that you never could do before. Okay, so the agenda is that we're going to talk about the Task Queue API, what it is, the idea of tasks and webhooks. We're going to compare push versus pull and the performance of these approaches. We're going to talk a little bit about idempotence and how queues are used and how throttling can be used. We'll also talk about names, task names, and estimated time of arrival. And during this talk, I'll also give you some example applications. One sends email, another one does schema migration, and another one for a write behind cache, which is a very high throughput, very high performance caching technique that can be used in a huge variety of ways that I'll talk about. And then finally, we'll talk about the future with some updates about where we are, where we're going, so on. So to get started, let's talk about the motivation. Why are we doing offline processing? So right now, Google App Engine is great for web applications. If you have a request-oriented, database-backed web application, App Engine works very well. But a lot of the time, people need to do more. They need to do batch processing. They need to do things in the background. And to that end, we added cron jobs to App Engine, but it's not enough. It's not fast enough. Real background processing would enable a whole new range of applications on App Engine that never existed before. So, entirely new functionality you couldn't have imagined of implementing on App Engine. So what is that functionality? Well, the question is, why do processing in the background? Well, the answer is it lets you do work continuously without any user requests coming in. So you can be doing computation all the time. Lets you incrementally process data, compute new results as the data comes in. And as we'll see later, it lets you smooth out load patterns, which lower user latency and have a bunch of other very nice properties. And so it's really a new style of doing computation on App Engine. That's what we're going for. So let me give you an introduction to how it works. So our first offline processing API on App Engine is called the Task Queue. We're releasing it under App Engine Labs, and that only means that we may change the API before we say it's done. And we wanted to do this to fix any errors that we may have before we give it a stamp of approval. And we also wanted to figure out how we're going to bill for the API to make sure that it makes sense for us and for our customers. So that's what Labs, App Engine Labs is. But today, the API is available for free as part of your App Engine apps for everyone. We have Python and Java APIs, so we did not have a Java API at launch. We do have one now. They work very similarly, so what you learn here will work in both. For free applications, we allow 100,000 tasks per day, and for build apps, we allow 1 million. And for both, there's a maximum execution rate of 20 tasks per second, and that's only because of the labs period. We plan to raise it much higher than 20 in the future. So what is a task queue? The idea is that you describe the work that you want to do right now, save that description somewhere, and then later on have something else or someone else do the actual work. Then the idea is that it's a queue, so the work is executed in the order it's received. And if at any time the execution fails, it'll be retried until eventually it's successful. So the smallest example you could have of a task queue is this. It's add a description of work to the task queue, right? Very simple. What's interesting is what that description of work is, and we'll talk about that very soon. But the benefits are it's asynchronous. You say, here's what I want to do it later. So you can put things off. It's very low latency. So writing a task to the task queue is about 3 times faster than the data store. So it's very quick. It's reliable. So once you write a task and say that you want to do it, it will eventually complete. It's guaranteed to eventually finish. It's also scalable. So tasks have no contention. So you can insert as many of them as you want at the same time. You can parallelize the actual work that the workers do. There are no throughput constraints. So you can go really super fast and do a lot of work with a task queue. And there are many features that extend this basic set of benefits, which is great, and we'll get into them. But to understand what a task queue is useful for, you need to think about history. So historically, Unix had an at command and a batch command. And lately, people use cron jobs and flat files very often to do their work. So every time they want to do some work in the background, they'll append to a file. They'll add a new line or something. And then every 15 minutes or so, they'll have a cron job wake up, and it'll read through the file and then do all the work and then delete the file. So it's kind of a poor man's queue getting through the local data. But this has a lot of problems. What if the machine goes away? What if 15 minutes is too long to wait? What if the file gets too big? How do you throttle the work so that the machine doesn't explode? You know, there's a whole bunch of problems. So task queues like this, they work, but they have a bunch of bad reliability and scalability issues. Now, there are better systems. You've probably heard of many of these task queue-like systems out there. There's ActiveMQ, WebSphere-MQ. I say star MQ here, just the whole set of them. There's Amazon Simple Queue Service. There's Microsoft Azure Queues. The Schwartz is one that's known. Twisted, Starling, Beanstalk. These are all queuing systems, messaging systems. Now, people often confuse messaging and queuing. PubSub messaging and queuing. They think they're the same thing. But they're not. They're not the same thing. So queuing systems maximize data throughput. So routers and data pipelines, that's queuing. And queuing fully saturates the network, fully uses CPU, fully uses disk. That's what queuing is for, maximum utilization. Whereas messaging has other goals, like maximizing transactions or maximizing the decoupling of your components. So PubSub systems are very good for large numbers of small transactions per second. This is why messaging, banking often uses messaging and trading systems often using types of messaging. The other thing is that messaging is good for publish and subscribe systems. So when one event has many consumers, so in an enterprise, an example of this is every time someone gets hired, one message goes out saying someone was hired, and then a bunch of subscribers receive that message, and one says, okay, give them a desk, and another says, okay, give them a computer, and another says, give them a bus pass, and on and on and on. So that's what PubSub systems are good for. So our new API is for queuing, not for PubSub. We're going for throughput. That's what we're going for. So keep that in mind. We also have a big difference in the way our queues work. So let's talk about traditional task queues and how they function. This is usually what they look like. You have new items going on to the end of the queue on this side. And then you have a series of workers that are alive at the bottom. And the workers constantly ask the queue mediator, which may be the queue itself, a database, a flat file, whatever. The workers say, do you have any more work? Do you have any more work? Do you have any more work? On and on. The answer is usually no. And so this has a series of problems. So first of all, the worker is sitting there doing nothing most of the time. It's polling the queue, which puts a lot of load on the queue. The workers also stay alive when they have nothing to do. They just sit there doing nothing. And you have a fixed number of workers, which means if you have a lot of load that comes in all of a sudden, you don't have enough workers to process it. So you need to go in as an administrator and add more workers to your queue. So it has scalability issues and administration issues. And further, there are limited optimizations that are possible. So you're polling. So some people fix this by simulating a polling interface with an event-driven one. That helps. So you can make it a little bit better. You can also use long-lived connections to make it a little bit better. But by and large, polling, it's just terrible. So traditional task queues they just waste a lot of resources. So we'd like to rectify that. We have something like 150,000 applications or more now. We need to be able to provide that kind of scale to all these apps. So what we do differently is that we push instead of pull. So no polling is necessary. And the way we push is using something called webhooks. So a webhook is a RESTful interface for doing work. It's just an HTTP request. It's used outside of Google and App Engine by other services elsewhere. I think PayPal has a very good webhook implementation they use. But the idea is that you describe the work to be done as an HTTP request with a URL and query parameters and a content type and headers, all the normal HTTP semantics you understand. That's the description of work. And many of our APIs in App Engine are using this style. Our incoming mail API uses this style. Our XMPP Jabber API uses webhooks as well. So it's a style that we're using more and more. It's just very useful. So like I was saying, on App Engine, our tasks are just HTTP requests. So when you want to enqueue a task, you say, what is the URL to hit? What is the body of the message? What are the headers, et cetera? And then later on, we will send you that same request exactly as you gave it to us. If your request gives us back a 200 response, then we're like, OK, that was successful. Any other response means it failed, and we should try again. OK. So let me give you a concrete example so you really understand. This is a queue for sending mail. Sending can take a long time. Maybe you want to do some extra work. So you may want to have a queue to do this in the background so users don't have to wait for the mail to spool up and go. So on the top, this is in Python. On the top, we have a standard request handler for HTTP requests. It takes a post method. And then what it does is it takes 3 parameters, 2 subject and body, takes those from the request, and then puts them in a mail message. It's really simple. Just sending an email. That's all we're doing. Below, we have an actual task queue call. So it says task queue add, and then it has the URL of this handler, which is work mail, and then it has the dictionary of parameters, to, subject, and from, and body. And that's it. That's an example. So I actually can show this to you live. This is kind of a, oh cool, that's there. Where's my mouse? All right, do we have it? So this is the wrong page. Sorry, I'll get to this one. All right, so this is funny. All right, so this is a sending mail demo. When I click this button, it'll enqueue a task, and then the task will happen later. It'll execute the task in a separate request. So usually mail sending takes 100 or 200 milliseconds. And here it'll be really fast. So I click send, and it's done. That's it. Very stupid demo, I'm sorry. But if you can read my email, you will see a new email in there. So if you can read my email, please let me know, because I'd like my password back, because I don't want to do that. Okay, anyway. Let's see where we are. Okay, that's a bad example. We'll get to a better one, but you get the idea. It's really simple. So here's how our queue works. So like I said, it's the opposite. We pull from the queue and then push to you. So new tasks come in on this side. We have a mediator that then receives those tasks and then sends them to your request handler. What this means is that if you have no tasks, you have no handlers running. We're never using CPU or any resources if you don't have tasks to run. So it's very efficient with your time, with your CPU time and your money. But similarly, if the load increases, then we will give you more threads. So we scale out, kind of elastically scale out the needs of your app based on your task load. So it has this great property of scaling up to the needs of your app. Now, there are some caveats, some detail. We will add worker threads depending on your workload. The maximum number of threads that you get depends on the throughput of your application. So the faster your app is per task, the more you get to run per second. Up to right now the limit of 20, but then later many more. And we plan on having a very high maximum rate limit for safety in the future, but we're going to let people run many, 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 many tasks per second. The other thing that's cool is that our tasks are integrated into our admin console as normal requests. So you get all the great things you know about App Engine request handling and administration from the task queue. You get application and request logs that you can search. You get dashboard statistics and error rate monitoring. And you also get the graphs to include the offline work. So you get a full picture of what's going on. And I'll show you more of that in just a bit. OK, so that's just the basic intro. So now we're going to get into some more interesting uses of this and details. So the first thing I want to talk about is idempotence. I don't know if there's a word in Russian for idempotence. I looked this up. I think it's just idempotence. It's a mathematics term. And what it means is that we have a requirement in the App Engine task queue that if you run the same task twice, you need to make sure that it can run twice so that it doesn't have side effects. So idempotent means being able to apply the same function multiple times to some data without any kind of bad side effect. So multiplying by 1 is usually a good idempotent operation. You multiply any number by 1 and you get back the same number again, right? Not always true, but usually. So in the App Engine task queue system, you need to make sure that your tasks can run multiple times. The reason is that there is a chance of hardware failure. So in our task queue system, if there's a hardware failure at a very particular time, there's a slight chance that your task may run twice. Very, very small chance, but it may happen. So it's important for you to think about that possibility when you build your app and to add a little bit of fault tolerance in there in your logic to ensure that that doesn't do something terrible, like moving too much money from one bank account to another, et cetera. So we do our best to give you tools to make your tasks idempotent, one of which is names, and I'll get into the details. But just remember that it's your responsibility to do this. So keep that in mind, that, that failure could happen, so you need to make sure that tasks are repeatable, they're idempotent. OK, so more details. We also have this idea of queues. So every task goes on a queue. And each task can only go on one queue for execution. We allow one application to have multiple queues. And the role of a queue is that it provides isolation and separation of tasks so that the tasks running in one queue don't affect the tasks running in another queue. And this is important for prioritization so that if you have one queue that's supposed to be high priority tasks, then it doesn't affect a queue that has low priority tasks. So you want to be able to keep them apart. And we also allow you to throttle each queue accordingly. So you might have needs to say, this queue can't go faster than 20 tasks per second. So people always ask me, oh, and this is an example of a queue YAML. This is how you configure queues. You give it a name and then the maximum rate. So you can have very slow queues, like a mail queue, or very fast queues. So why do you want to throttle? Well, there's a few reasons. First of all, maybe your queue combines work periodically into batches and then executes it. Or maybe you want to ensure the stability of your workload, like your CPU, your bandwidth, or your money. Or Or maybe you want to make sure you don't exceed the maximum writes per second for an entity group. That's a really common one. People write to the data store too quickly, and they need to make sure that they slow it down so that it's reliable. Another one is if you have a web service calls you're making to another site, and you don't want to attack them, like send them too many requests, you can use a queue to throttle that to a certain rate. Same thing with email and spam email. And like I was saying, it also lets you prioritize work, so you can have fast queues and slow queues. So it gives you a lot of flexibility and control over how your tasks are running. And so the very complicated picture of this is this one, which is kind of has too much going on. But basically the point is that the queues are in the middle, the tasks are on the left, and the workers are on the right. And each task will go to a worker, but the way it gets to that worker is independent of which queue it's on. So you might have a high priority queue, medium priority queue, and a low priority queue. And any task type going to any worker can go through any queue. So the queues have nothing to do with the contents or payload of the task. The queue is specifically a mechanism for isolation and throttling. That's all it's there for. It's just for control. So that's the distinction between tasks and queues. Okay, so let's talk about a concrete example. So schema migration is something that I hear from users a lot. They have an old schema and they want a new schema, and they want to move all their data from one to the other. So without the task queue right now, you can do this using a cron job. The cron job would step through entities, and it would copy them over to the new style. And then maybe you would store a cursor in memcache or in the data store, and you'd slowly go through the data. But that's really slow. The cron jobs just aren't fast enough. Alternatively, you could use the remote API or the bulk loader to download the entire data set and then re-upload it. But that's stupid if you have a lot of data, and it's also very slow. So luckily, the task queue API lets us fix this. So you would define, this is a lot of words, I'm sorry about it. So you would define a worker that migrates the next n entities. It would retrieve them, modify them to the new schema, save them in the data store, just like the cron, except when it's done migrating, it would enqueue another task to start after the current position to then migrate the next batch. So you kind of you'd increment across, migrating a batch at a time to the new schema until you got to the end. And the thing that's nice is that since any task will be restarted if it fails, you're guaranteed that it will eventually get to the end. So let me show you that in action with some real code. So here we have the first user kind at the top. These are two ORM models in the data store. There's one kind which has names, and another kind that has first and last names separated. The only difference is the space. So the top kind has the whole name on one line. The other has them separated into two. And then I have two migrating functions, second from first and first from second. And all it does is migrates from one kind to the other by combining on a space or splitting on a space. Very simple, right? Really stupid. Okay, so this is where it gets hard. So this is the actual migration function. So now what this does is what I was describing. I do a query on the from kind. Let's say this is the first kind. I'll skip this next bit, but I say from kind dot all. And then I say fetch 10, old equals query dot fetch 10. And then if there's nothing left, if old is empty, then I say, hey, I'm all done. Otherwise, I find the last item in my list, and I say, okay, I will start next time after this point. Then I say, here are my new entities, new equals migrate each one. Then I put the new ones in the data store. I delete the old ones, and then I add a new task, like I said, which says do more migration, but the starting point will be at the point after all of this data on this entity kind. Okay, so it's just kind of continuation passing. It's moving forward. And that top part that I skipped, where it says if start query.filter key is greater than so-and-so, that is what gives me the offset into my query. So that's an offset. That's all that is. It's like paging. it gives me a start in my query with a key. So I can say, give me everything after this point. So that's how I chunk through my data. So I can show this in action too. With another silly demo. Let's see. Oh, okay. All right, so here are some funny names here. Sorry if they're silly. These are the first kind where it's the two names next to each other with a space in between them. And then I have the ability to migrate from first kind to second kind. So I click this button, and then it should start moving them across. So if I reload this, now you see they've all moved to second. Chunking through the data. Maybe I hit a little bug, but it'll chunk its way through. Depending on how fresh this app is, it'll go faster or slower. But you can see that on the top I have them with no comma, and on the bottom I have them with a comma. So it's migrating between the two. There, so it's done. So that's like a simple schema migration. This is just a small demo, and you can do a lot of things to make it faster and parallelized and so on. Okay. So let's talk about some other advanced features, and then we'll get to the best example of all this in action. Estimated time of arrival, ETA. This is a way of saying this task should be executed in 10 seconds, in 5 minutes, or this task should be executed on this date at this time. So it lets you specify exactly when you want the task to happen. And it's different than other systems. Amazon SQS and many other task queue systems have a visibility timeout. This is not a visibility timeout. It's very different. Visibility timeouts have to do with locking and exclusivity. There's none of that in our system. You don't have to tune your visibility timeout. It's all done for you. An ETA is just a way of specifying when things should execute. So it gives you fine-grained control, like cron, over when tasks run. So it gives you a lot of distinct control. And it also lets you do cool kinds of prioritization. So if you have a task that you know doesn't need to happen for another few hours, you can schedule that task to run during your low time on your app. So if you know that no one's online after 4 a.m., then you can schedule tasks to run at 4 a.m., and then they won't affect the rest of your application as it runs. So that's the idea. You can also use it to do all kinds of periodic functions like clearing caches, flushing buffers, doing incremental reports, sending emails, any kind of heartbeat, high throughput heartbeat, you can do that. The other advanced feature are names. So this gets into the idempotent stuff I was talking about. So when you create a task, you can also give it a name. And if you don't supply a name, one will be generated for you. But what's really cool about a task name is that every time a task completes, its tombstone will stay around. And if you add a task with the same name as one that's already existed, then the task won't run again. That's the idea. So adding the task will do nothing. And the benefit of this is it gives you only one semantics. So, when you say migrate these entities to the new schema, then you would click a button to do that. And if I click the button again, then I would migrate it 2, 3, 4 more times, and that's bad. So using key names, I can ensure that clicking that button once will only ever happen once. And it gives me just a really easy way to implement that. And there are many applications of only one semantics, but that's what this does. However, as I've said, you have to watch out. There's still that tiny chance of multiple execution. So even though you will get only one semantics, there's still a chance of hardware failure. So you need to implement your tasks with idempotence. So remember that. Okay, so let's get into a really good example. This is my favorite example that really shows what the task queue can do and the real effect it has on you as an application developer. And this example is something that you guys can start using in your apps, pretty much today, which is really, really useful. So what is a write behind cache? I need to give you some background so you understand. So a write behind cache minimizes database writes by repeatedly flushing a cache. The idea is that you write data to a cache, and then ever so often, like a memory cache, like memcache, and then ever so often you will read from the memcache and write it to disk, put it in the data store. Now, that simple idea is amazing because database writes are no longer a function of user load. So you might have a lot of users coming in, updating data, and all of those updates will go to the memcache, which is super fast. And then maybe once a second, you'll read from the memcache and store it in the data store. So there's no longer a relation between your front-end requests and your data store requests. You can do 100 cache writes a second and only 1 database write per second, which makes it a lot cheaper to run this kind of system. And lower latency for your users, more scalability, et cetera. The problem, the trade-off, nothing's free, right, is that there's a small window where you may lose cache data. Very small window. But most of the time, if you're doing this, that's OK. And I'll show you where that window is. So here's my silly diagram. Time goes down. This is a sequence diagram from left to right. On the left is the user, and they're initiating a write through your web application. So they click a button. It goes to your request handler. Your request handler then writes some information to the cache. Maybe it increments a counter, whatever, puts some data in the cache. And then immediately the request handler returns back to the user. Then possibly the request handler adds a task to the task queue saying, hey, I updated the cache. Maybe do some database work in the background. And then it immediately returns. Because task queue writes are very fast. So this top part of the diagram is very quick. Now, the task eventually will be dispatched, and the task will run. And then that task worker will read from the cache, and then write the cache values to the database in batch. So this is the decoupling, the separation of the user requests from the database requests. And that's why this is so powerful. There's actually no connection between the two, like no direct connection. The problem is right here, where the cache could fail, this red spot. Now, you can narrow this window as much as you want. You can make it 50 milliseconds, or 100 milliseconds, or a second. Depends on how important your data is. There are many things you can do to mitigate the size of this window. For instance, if you have a client that has Ajax or GUID or jQuery or some kind of smart client, the client can detect the failure and be like, oh, the cache died. I need to send this write again. You know? So there are many smart techniques you can use to minimize that failure window as much as possible. So be sure to try them out. So let me show you some code. So let's use this idea of a write behind cache and make a hit counter. If you've ever tried to make a counter on App Engine, it's way harder than it should be. And that is because of the way our data layer is. Our data layer is meant to be wide in scale, and the trade-off is individual row throughput. So if you've tried to make a counter on App Engine, you have to use sharded counters to get the throughput you need. You have to split your counters into multiple counters. You have to partition them so that they don't affect each other, so they have high throughput. And with the sharded counter, you have no control over the throughput. You still have your incoming request locked to your database throughput, so it's problematic. But with the write behind cache, you're in really good shape. So every time there's a hit on a page, you increment a counter in memcache. That's like 5 milliseconds or less. And then ever so often, you copy those memcache values to the data store with a task. And then you can use the queue throttle rate to limit how fast you write to the transactional group. So if you know your transactional group cannot go faster than once per second, then you just set your queue rate at once per second, and you're set. And then when you want to read the value of the counter, you can either read from memcache or from the data store. They should both be pretty close to each other. So you have a lot of flexibility here at doing just a simple hit counter. And you can do other stats exactly the same way. So let me show you the code. So this is what the client request would do. I have a ORM model at the top. It's a counter with a single property, which is the count. That could also be sum, average, whatever. Then below I have a class which is the handler, and this is what the user request runs. So the first thing it does is it has a key. Let's say it has a key for the counter to increment. Okay, and it'll call memcache increment on the key, and then it'll say, if that's not in the cache, the initial value is 1, so we start counting at 1. And then, so that incremented in the cache by 1. So that's the hit counter in memcache. And then what it does is a memcache add. Now, those of you familiar with memcache know that add is kind of like a mutex. It's a lock. It effectively runs like a lock, so that only one requester can add an item at a time. And once they've added it, all other requesters will get back false. So the memcache, if memcache add says, am I the only one who's added this item? And it'll say it back a true value, if so. And that means, it's equivalent to setting a dirty bit on this cached information. So that's why I have the dirty string in there. So once the dirty bit's set, I know that I should add a task to the task queue, and that task should call to my worker with this key. And so I describe the work there. The URL is the worker, and the parameters are the key to increment, the key to flush. So that's all there is to it. So then on the worker side, this is my offline worker. It receives a post request. It gets the key of the stat I'm trying to increment. Then it deletes the dirty bit, which basically unlocks the lock, so that future locks may also grab the lock. Then it gets the value from memcache. And if the value is still present, which it might not be if the cache was evicted, it's possible. So it'll say something in the log. It'll have an error in the log if that's not the case. But otherwise, it gets the value out of memcache, creates a counter, and then puts it in the data store. And that's it. That simple code decouples incoming throughput from outgoing writes. It's vastly important. For some people I've seen running sharded counters, this can save them many dollars of CPU time for every 1,000 counts or whatever it is, depending on what you're doing. And you can do all kinds of really cool aggregations like this. So I really recommend you look at this simple idea of a write behind cache and apply it to many things. After you think about it for a while, I don't know if you've heard, there's a saying that's, when you have a hammer, everything looks like a nail. That's kind of this. Once you have a write behind cache code, every problem you hit in App Engine, you're like, oh, I'll give that a write behind cache. I'll give that a write behind cache. It's a very good answer for many, many problems. So let me show this in action. See if this works. Okay. Okay, so this is, that's probably a swear word, huh? I don't know. So this is a set of counters you can count. And if I type in one, say foo, and click increment, it'll go up to 5. Now you may say, Brett, I can code that too. It's very simple. That's a stupid demo. And that might be right. So let me show you that it actually worked. So this is using a write behind cache. So these are my logs on the task queue. So let me restart. Okay. So let me show you this. So this is my first request from Slatkin. Okay, that's what loaded the counters page. And you see it's a GET request right here. Then the next one was a post. And this is where I incremented the counter. Now, here's where it gets really interesting. I don't know if you can see these times, but the next request is the offline worker. This is the write behind cache task that was running. And you'll see my request came in. I clicked the button at, these are Pacific time, so 4:45 a.m. I'm jet lagged, yes. And 23 seconds, 0.72. 727. So that's when I clicked. And the background task started running at 23.758. So within 30 milliseconds, the other task was enqueued and started executing. What that means is that tasks are reentrant. They will actually run at the same time as they're added. So many times you'll call task queue.add, and before it comes back, that task will already be running. So for programmers, that's very similar to spawning a thread. This actually lets you have parallelism in your application. But it does it in a way that's very scalable and controllable, which is better than a lot of traditional multiprocessing. So in this case, though, you remember how it went from 4 to 5 before I reloaded the page? That was, you thought maybe I was lying. What happened was that that request finished before I went to America and came back. Because my browser's connected to some stuff over there. So I have to wait the whole time to go all the way there and back again, which ended up taking, looks like 200 and some odd milliseconds. So then it took me longer to reload the page than it did for the task queue to execute completely. And that's why it looks the way it does. But for you, what that means is that task queues run very quickly in a very low latency manner, which is really cool. It lets you do all kinds of very interesting things relating to stream processing and workflow and on. If you want to know about some more examples and possibilities, there's a really good example of a workflow pipeline, if I do say so myself, which is part of the PubSub Hubbub project, which I'll be talking about at 4:30 in some other room, maybe room 4. And that's a pipeline that does stream processing on Atom feeds and RSS feeds. So that uses the task queue for everything, and it does a full real-time workflow of stream processing using our task queue API. It's very cool. You can also do all kinds of materialized views, aggregations, other types of math, and updates using the task queue API. So it's great for many of the problems you've hit using App Engine in the past. So let's talk about the future just a little bit, and then we'll wrap up for some questions. So if you're doing batch processing, the task queue API is great for small data sets. It's good for 100,000 rows or less, but we really need better tools for massive parallelization and high throughput of data store entities. We need richer features for aggregations and statistics. We need better monitoring consoles. We need better debugging tools. So this is just the beginning of what we're doing on the App Engine team for offline processing. We've got a lot more on the way. So we want to be able to support huge data sets with millions and billions of rows and make that manageable for developers. So that's where we're headed. We're also planning to support a MapReduce abstraction. So if you have not heard of Google's MapReduce abstraction or the Hadoop project or many of the other ones like it out there, I encourage you to look that up. We would like to have our own for doing real high throughput data analysis. But we really need more tools. We need an intermediate storage API. We need a better sorter for reducing. And there's a few other things like that. And the difficulty also is that we want our MapReduce implementation to work very well for small data sets like 50,000 entities and also very large data sets up to a terabyte and larger. So that's what we're focusing on right now. And we're also keeping our eye to the future for work on workflow, pipelines, stream processing, online analysis of data, very high throughput data queuing systems, like I was talking about before. So that's kind of what's in the future. And we'll be putting more of this on our public roadmap as it gets closer. So to wrap up, and then we'll have questions. Use the task queue API. It will make your app faster. It'll lower your latency. It'll scale your app in a better way and reduce your costs. It'll let you do things you never could do before. And when you start using webhooks for easy debugging, you really can't go back. And let me give you a quick example of that. All of these workers, they're just taking HTTP requests. It's just form URL encoded data or HTML post body. It's very simple. So if you want to debug your task queue, you can actually send it requests. You can send your worker requests either from your browser or from your command line. You can simulate a task running on the queue. So if there's this one task that's always breaking on you, you can actually reproduce it and debug the problem. So it's just, that's why we chose this method of doing work, because it's an idea that we all understand as programmers very well and that we've dealt with in web programming many times. So definitely take advantage of that. So yeah, any questions? And if not, thanks for coming. Yeah.
If there a way for the application to check for the status of the started task queue task?
Okay. Right. So yeah, can the application determine if the task is running or if the queue is running?
Yes, is it completed or not?
Right. So that's a great question. So yeah, can you know if the task is done or if the queue is empty? Right now there's not, but this is something that we're actively working on. We'd love for you to be able to say, when all tasks in this queue are done, tell me somehow, let me know. And you need that to do pipelines and flows properly. So not yet, but we're working on that. We're also working on other features around getting task status and flushing tasks. And actually, I can show in the admin console now, we have a task queues tab here. So we have the ability to get this information for the UI, where you can see the queues you have and the oldest tasks and how the tasks are running. So you have more introspection into the queues now, and you can actually see here's a task with a name, and here's what it needs to do, and here's its payload. So you can do introspection, and you can also delete it if you want to.
And we can do it through the API.
So right now this is just through the admin console, but we would like to give you the ability to do all of this in the API as well.
Thank you.
Yeah. Any other questions? I see one over here. I see one over there. I don't know how many mics we have. Right there. Oh, he's got a microphone. Yeah.
Okay. Oh, I got two questions. First is, you are limiting the number of tasks per day, but you don't seem to have any limits for the granularity of tasks or how long they are running, right? In the example that you gave about paging, you could use a different amount of different page size, like get 10 issues or process all the database in one task. So is there anything?
Yeah, so yeah, the question is, do we limit how long the tasks run for when they're running on the task queue? And then maybe you could get around those limits by changing the size of the page when you do a schema migration. So the tasks running on the task queue fall under the same limitations as the rest of App Engine, which is a 30-second request limit. So the tasks may run up to 30 seconds at a time. So that's how you would specify your page size. You tune it to a 30-second runtime, essentially. And then, like I was saying before, the throughput of your tasks really depends on how long it takes for each task to run. So for instance, if every task you have takes 30 seconds, then you're going to have fewer of those running simultaneously than if each of your tasks takes 200 milliseconds. So we scale the throughput. We find the right balance on your app of the throughput versus kind of like how chunky your task is. And so that's our system does that automatically, and we're tuning that and making that higher throughput as time goes on.
Okay, thank you. And the other question is, how do you deal with failures? Task may fail, for example, if it exceeds the 30-second timeout, or it may fail because there's a bug or something, so it will consistently fail if you run it next time. So
yeah, so how do you deal with task failures? So the answer is that if you log your task status, it will go in your application and request logs. So you can see that it's failing. You can even filter your request logs just based on the path of that request. So you can actually hone in on just the tasks that have failed. And now in our admin console, you can actually look at those tasks and what URL they were going to. So you can see, oh, this task has failed 20 times. I wonder why. And you can find the logs. So you use the common facilities for all App Engine apps and all App Engine requests to do that debugging. So the other thing is, so that's the debugging. And then the retry failure case, we will automatically retry the task until you give us back a 200 response. So we will back off exponentially, but we will continue to try running that task until it's finished or until you manually delete it in the admin console. Okay.
Hello, Brett. In your examples, you use memcache as intermediate storage. But as far as I know, memcache can lose data on various conditions. So is there some way to deal with this and to guarantee that our data isn't lost between the moment we put it into the cache and in between the task is run?
So right now, there isn't. I mean, that's the trade-off. You use Memcache because it's much faster, much cheaper, lower load, on and on. It gives you that horizontal scaling. And in the future, maybe we'll have some other kinds of data backends, but that example is specifically trying to maximize the throughput of a system that has a constraint, which is the data store throughput. So although Memcache can lose data, if you do some experiments on your own cache size, you'll see that our Memcache is actually pretty reliable. We do evict the cache ever so often, but we try our hardest to minimize all evictions to basically hardware failures. So give it a shot.
So the chance to lose data is too small to...
I mean, the thing about Memcache is that it's a least recently used cache. So if you have a hot row, a hot key that you're constantly updating, it'll stay in the cache. And so that's pretty reliable. Yes, it still can be lost. It's possible, but it's worth it for these cases.
Okay, thank you.
Yep. I think we have time for one more. Yep.
On the slide with data migration, you make a request that have few assumptions. First, assumption that key is always increasing, and second is that data is ordered by that field. Is it true? If start query filter key greater than key from parameter.
Yeah, so under key is a special parameter, refers to the primary key of the entity. And your data is always sorted by that key, in addition to any other sorts you may specify. So key is the big table row name. It's the primary key of the data. And so yes, it will always be in this order, and so you can always iterate through your data in key order, ascending. It'll always work. That's part of our data store design and how big table works.
So we can rely on that.
You can rely on that. Yep.
Thank you.
Yep. Okay, so I think that's it. Thanks a lot for coming. If you have any more questions, I'll be here for a few more minutes, and then please come to my talk on PubSub Hubbub if you care about the real-time web and want to see where that's going. So thanks.